squared times 20 seconds equals the velocity. And then you end up with negative 15 meters per second squared. But that is only the velocity at the bottom part of this graph. To find the actual velocity at that time, you need to take the velocity at this point before it dropped. And consider, because there's no acceleration here, acceleration is constant. So up until this point, acceleration is also 20 meters per second. So you take the initial velocity at that point, which is 20 meters per second, and then subtract the 15 meters per second squared to get 5 meters per second, or not squared, 5 meters per second, 5 meters per second at that point. Then part B asks for the distance traveled in the first 20 seconds. So to get that, I graphed the velocity versus time graph, which looks something like that for the first half. And I only used this graph for the first half of to find the first half of the distance. For the second half of the distance, I used a kinematic. So to get the first part, I found the area under the curve here, which would be found by using area equals 1/2 base times height, where 1/2 and then the base is 10 and the height is 20, which I found using the information we found in the previous section. So then you end up with 100 meters for this area. To find the second section, area is just finding the area of a rectangle. So you have 20 meters per second times 5 seconds, which also gives you 100 meters. To find the last part, instead of using area under the curve because it was kind of funky, I used a kinematic. So I used delta x equals 1/2 vi plus vf times t, and used the information found above that to solve this kinematic. So you know you're trying to find delta x, and you have 1/2 times 20 meters per second plus 5 meters per second times 5 seconds. So delta x ends up being 62.5 meters